In this session, we will control the light sensor and we will receive analog input through the ADC. For the input, we will use pin A3, which connects to pin Y12 when inserted here. So, this pin Y12 will be connected, and you should plug in a 3-pin harness cable here and connect it to the light sensor. Then, since we will also display the values on the OLED display this time, please connect it like this. In our last session, I took the step of opening the code, which was an important part of our workflow. Now, I am going to take a different approach by erasing the current code. This will give me the opportunity to start over and try writing the code again, incorporating any new ideas or improvements I have thought of to the SS1306 SSD is a reliable component in electronics, often called cache for its efficiency. To set it up, configure the board's SCK, serial clock, and board loss parameters accurately to ensure optimal performance and avoid data errors. Next, initialize the device with the lay address 0x3c, a common practice for effective communication within the system. This address acts as a unique identifier. After initialization, set the analog input mode to A3, known for its precision in capturing analog signals, ideal for high accuracy applications. By following these steps, users can enhance the SS1306 SSD's functionality and longevity in their projects. To ensure the proper functioning of your electronic project, it is crucial to accurately read the light sensor connected to pin A3 on your microcontroller. The light sensor is a vital component that measures the intensity of light in the environment, which can be used for various applications, such as adjusting the brightness of a display or triggering an action when a certain light level is detected. At this point in your project, you should focus on obtaining a reading from the sensor. Specifically, you need to check if the sensor's output is approximately 15. This value is significant because it indicates a specific light condition that 15, as well as 16. Next, we will display the ADC value directly here, which is a 16-bit value. ADC stands for Analog to Digital Converter, a crucial component in electronics that transforms analog signals into digital data. The ADC value read as 16-bit will be converted to a voltage value, which is 3.3 volts. This transformation is essential for digital systems to process real-world signals. The 3.3 volts is a common reference voltage in electronic circuits, ensuring compatibility. We will be displaying how many volts it is, based on the reference of 3.3 volts. To display the ADC value accurately, we need to represent it as a 16-bit number. For example, consider the value 6535. This value should be displayed up to the second decimal place to ensure precision. Additionally, it is important to note that the reference voltage level is 3.3 volts. This means that the ADC value is scaled according to this reference voltage, allowing for accurate analog to digital conversion. By doing so, we ensure that the digital representation of the analog signal is both precise and reliable, which is crucial for the system's performance and accuracy. The process begins by displaying the voltage values, which are measured in volts. This is a crucial step in understanding the electrical characteristics of the system. Although the measurement is not perfectly precise, it provides a general indication of the lighting conditions. For instance, when the voltage is high, it suggests that the environment is bright. Conversely, a low voltage reading implies darkness, while a moderate voltage indicates average lighting conditions. These interpretations are based on the ADC, or analog to digital converter, values, which convert the analog signals into digital data that can be analyzed. The ADC plays a vital role in this process by ensuring that the voltage readings are accurately translated into a format that can be easily understood and utilized. The final segment of this analysis involves categorizing the lighting conditions into 3 distinct groups: bright, dark, and average. This categorization is essential for applications that rely on precise lighting conditions, such as photography or plant growth monitoring. By understanding these categories, users can make informed decisions based on the voltage readings provided by the system. If the value is between 0 and 2184, it indicates bright. From 21840 to 43680, it is normal. And anything above that indicates dim. I will set it up to display like this. I have saved it, and now I will check it. Now, as you can see here, first you can view the original value as a 16-bit number, and you can see that it has been converted to a voltage value. If I point my finger at this light sensor, the resistance value increases to about 56,000, and the voltage value also rises. If I bring my finger closer, it changes to bright, and when I remove it, it goes back to normal. If I touch it with my finger, it shows weak. This is how you can check the values of the light sensor. In this session, we used CircuitPython to check the values of the light sensor. I will see you again next time with different content.